Hey guys, this is the first review video we've done, so let me just give you a quick heads up here in case you didn't catch it in class the other day. You need your notes out as you watch these things. The notes for chapter 13 that you just picked up today, sections 1, 2, 4, and 7. I am skipping some sections. We are going to go over those other sections in class. Those skipped sections will not be on the review quiz. The skipped sections will not be. But these 4 sections are all things you learned in chemistry already. You should already know them. And that's why I'm going to review them real quickly so that we can take a quiz showing your proficiency in those things. So, first things first, molarity. Molarity is something we learned last year. It is how many moles have been dissolved into a solution. And so that's the moles divided by the volume. If you ever feel like you can't remember this equation, this guy in the red box is given on your equation sheet. It does say molarity is equal to moles of solute per liter solution. You need to make sure that you're representing the right solute. Remember, solute is what you dissolve in the solution. It's what you dissolve in the solution. So if you dissolve 2 moles of calcium chloride, well, there's 2 moles of calcium in the solution, 4 moles of chlorine in the solution. Why 4 moles of chlorine? Well, as you dissolve 2 moles, you get 2 extra moles of chlorine. So you need to be aware of the compound. Is it asking for the whole compound? Is it asking for a specific ion? You've got to read the question carefully when it's asking for the moles of which solute. Anyway, and then the volume is just the total volume after everything's dissolved. So we talked about equilibrium a lot last year. This kind of explains why reactions don't actually reach completion a great deal of the time. And what happens is when a reaction occurs, say this reaction here, the reaction's moving forward or to the right, making product, and you might reach a point at which the products start to build up and decompose and go backwards and make reactants. So reactants can build up products, and then products could break apart and make reactants and go back and forth and back and forth. And so we have double-sided arrows now instead of single direction arrows. Well, eventually that forward and backward balances out. And I don't mean stops balances. I mean the speed forward and the speed backward become the same. They become the same, and that's what we call dynamic equilibrium. It's still moving, but it's moving in equilibrium, in equal rates forward and reverse. Think speed forward, speed reverse is equivalent. What is true about the initial rate of forward versus the initial rate of the reverse? Well, initially, let's just imagine this. Initially, Mr. Murphy puts hydrogen in a bottle. He mixes it with iodine in a bottle. And then he lights it on fire or whatever is needed. And the reaction goes. Initially, there are only reactants. There's hydrogen and iodine. There are no products yet. Once these react, he politely shows up and says, hi. And then, if you get too many, not literally 2, but just if the products really start to build up enough, you might get a reverse reaction. So the initial or beginning rate of the forward reaction is much greater than the reverse. So the speed of the forward is greater than the reverse, but it's only greater right now because there is nothing in reverse. What is true about the rates of the forward and reverse reaction in equilibrium? We already said this. They are equivalent. One thing we need to stress, though, is that while the rates are equivalent, that doesn't mean the molarities are equivalent. The molarities do not have to be equal. In fact, they almost never are. That's so much that I put, let's put molarity of reactants versus molarity of products. They're not really ever going to be equal. I can't think of an instance where they would be 100% equal. Quite often, it's heavily tilted one way to the other, like 0.2 to 0.00005, just drastically different numbers one way or the other. Why does equilibrium occur? There's a number of possible answers to this one. Maybe the products are unstable, the products are really stable. If the products are really stable, let's say that this product was really stable. These guys are combining together and making HI. If they're really stable, they're not going to break apart and go backwards. So then equilibrium is going to have tons of product, really high molarity of the product, very few reactants. Reverse scenario. What if this product is highly unstable? Well, then these guys combine together, make HI, it's unstable, bounces right back, and you get these products back. It just depends on which ones are more or less stable. Factors that can determine the equilibrium position: concentration's a big one. States of matter, like if something's a solid, liquid, gas, or aqueous, those have a huge impact we're going to discuss. Temperature, of course. If you heat things up, they're moving around faster, they collide more. Cool them off, they collide less. That changes whether it shifts to the right or to the left. Nature of chemicals. Gasoline I like to think about in this case. Gasoline's a big organic compound, and it's kind of stable. But over a couple of months, this big organic compound, which is way bigger than HI, this big organic compound slowly breaks apart into carbon dioxide and water and reverses the reaction that took millions of years to make that gasoline. All right, here we go. Setting up mass actions or equilibrium expressions. Equilibrium expressions were like the bread and butter of this chapter last year. You had the products. Products are on the right side, go on top. Reactants are on the left side, they go on the bottom. This is just like the real world, the right people controlling over top of the left people. That's funny in my opinion. So it's always the products over the reactants equals K. HI is a product, so it's going on top. There's two of them, so HI is squared. Okay, let's look at that. 2 for the coefficient, HI squared. That's not a coincidence. H2, I2, they are being multiplied together, not added. Not added. That doesn't look like not added at all. Let's do this. Make a addition symbol. Not added together, they are multiplied together. So, very common AP Chem question. There'll probably be 1 or 2 or 3 of these in the free response. Set up the equilibrium expression for this reaction. Here's the 3 equilibrium expressions for these reactions. Notice that it's just set up. These are the products, they go on top, reactant on the bottom. These are not added in here, they're actually multiplied in there. That's an 8, so that's to the 8th power. Again, these are being multiplied, products, reactants, setup is done, equilibrium expression, bam! And so this is a mathematical expression to represent when equilibrium is achieved. That's what K is, equilibrium constant. K for constant, because that's how you spell it, right? It should be constant. The products divided by the reactants equal the same value every time. That's what constant means, same value every time. So also, when we see brackets like this, that means molarity, even if you can't fit it inside the brackets. Brackets means molarity. So here I've got a couple set up. K is, it's the same problem we've been dealing with. Let me just move these orange boxes. They're kind of irritating me. K is the equilibrium constant. I wrote down the equation, products over reactants, and I carefully read the problem. H2 is 0.106. H2, 0.106, HI, plugged all these things in. Oh, that's squared. I gotta make sure I square that number. So this number squared divided by those two equals 710. Okay? Again, that 710 would be the products ratio to the reactants. 710 over 1. Oh, there's a lot more products than there are reactants in this problem. Number 3 is the same idea. Just want to kind of go over the language of this question using the same reaction as previously. Oh, there's K. The equilibrium concentration is H2I2. Are this respectively. That means that in the same order as it's written. H2, I2. In the same order or with respect to each other as they're listed there. So when we plug them in, we know which goes where. That's a weird way that people often tell you who is who. It'd be like, grades are A and B, respectively, for Billy and Johnny. Why didn't you say they had an A and she had a B? Whatever. So with this problem, we're given the constant, we're given two of the values, solving for the missing value. One tricky thing about this missing value is it is a squared value. So if you just cross multiply these over here, first multiply them and then switch and do the algebra, you will have only solved for hi squared. You have to take a square root of everything to get to just hi. So move them around, then take a square root. You've got the concentration of hi. What if you're working with the reverse reaction? Well, let's just remember this reaction here had a constant of 710. H2I2 makes 2Hi, 710. Well, that is the products over the reactants, 710 over 1. If the reaction is reversed, 710 is no longer true. It's now the reverse reaction. So for this reverse reaction, it would be 710 to the negative 1 power, or K is equal to 1 over 710. All this means is that K reverse is equal to the inverse of K normal, or K forward. This is not like an equation. This is just a concept that if you end up reversing the reaction, you could take an equilibrium constant's inverse, and it works just fine. 13.2, this section, we're going to kind of skip this whole thing for right now. I'll talk about it in class because we didn't do equilibrium constants with pressure. Feel free to pause and jot this down. But this part won't be on the quiz. 13.4, heterogeneous. This just means that there are solids and liquids and different states of matter involved in. And some states of matter are easier to deal with than others. Solids are very easy to deal with. Solids get replaced with the number 1. So look at this. We have a gas, a solid, and a solid. These two are the products. They go on top. This is the reactant. It goes on the bottom. So there's our equilibrium expression, right? That's the expression. Except 2 of them are solids. We're going to replace both of the solids with 1. So basically, for this reaction, K, the equilibrium constant, is equal to CO2. So as the CO2 is too high, the reaction will shift to the left. If the CO2 is too low, it'll shift to the right. K is dependent on how much CO2 is. The solids don't impact the equilibrium position. The same thing is also true for liquids. So for solids, jot this down, or liquids, we enter 1 for their concentration. If the value is 1, it doesn't matter what the coefficient is. If the coefficient's a 5, what's 1 to the 5th power? It's 1. So it doesn't matter what the coefficients are for solids and liquids. They get a 1 thrown in there, you're done. So these setups here are pretty easy. I've done A and I've done E. Barium hydroxide solid. Barium is aqueous, 2 hydroxides. So I just replaced the solid with a 1. So you have barium times hydroxide squared equals K. And I did E. Everything was aqueous in E, so I just did that one so people wouldn't think that there was something else going on. But anywhere you see a solid, you don't really cross it out. That's not a good idea. But just jot down a 1. I always jot down a 1 because I want to make sure I took care of it. Now here, this water versus that water. What's the difference between those two waters? 3, 2, 1. This water is a gas. That water is a liquid. So this water is going to be in the expression as H2O squared. This water would go in as a 1 to the 6th power. Why? I like to conceptually think about the mobility of these things. They are objects. They do really exist in nature. Like with this scenario here, you have a chunk of calcium carbonate. Oh, that's chunky, right? And it is breaking apart. It is giving off carbon dioxide. And since this is a gas, that carbon dioxide is actually floating around the world and bouncing into things and, colliding with stuff. If that if the calcium oxide, also make calcium oxide. And if that carbon dioxide that's just been bouncing around everywhere happens to collide with the calcium oxide, it might then reverse the reaction. But the calcium oxide is a solid. It's not mobile. It is not going anywhere. The CO2 has to come to it. If we were to add tons more CO2 into the container, pretending like the board's a container, as these guys are going to bounce around a lot more and they're more likely to hit the solid calcium oxide, not the reverse. The calcium oxide's not moving. The carbon dioxide is moving. So gases are mobile and therefore impact equilibrium. Solids are immobile and don't impact it. That's why we replace them with a 1. We apply the same logic to liquids because for the most part liquids sit in the little puddle that they are. Aqueous ions are mobile. They're just mobile inside the medium in which they're dissolved in, which is generally water. So those aqueous ions are floating around inside there. A scenario, get rid of all this stuff. A scenario like F, I'm going to imagine there's a beaker. The bottom is this solid chunk. The liquid water is what it's all dissolved in. And then these things are floating around as ions inside there. And these guys are mobile inside the water. And therefore they might collide with each other and shift back. But the aluminum nitrate and the water aren't really that reactive or something. That's a pretty crazy equation there. All right, moving on. 13.5, we're going to hit this in class. It's a little complicated, more conceptual. We've got to talk about Q. More of that. Feel free to jot these stuff down before we go over it. Let me zoom in so you can see this, but we're not actually going to go over it here in this video. You might want to just jot down these numbers, but we're going to go over this stuff in class so it's not in the quiz. Same thing here. Let's go to something that will be on the quiz because you don't have all night to watch this video. Le Chatelier's principle. Le Chatelier was the man who discussed shifting of reactions. So we have a reaction that is in dynamic equilibrium. So this reaction's shifting back and forth in balance, same reaction rates forward and backward, and then someone comes along and adds nitrogen. Nitrogen is added. Now there's too much nitrogen in there. There's too much of this nitrogen and the reaction's no longer in balance. So in order to get the balance back, some of this nitrogen has to disappear, but it can't just leave the container. The container with the nitrogen, the oxygen, and the nitrogen monoxide is a sealed container. Well, it can't be completely sealed. Let's put a syringe or something. Here's a little syringe. So this nitrogen is squirted in through the syringe, and now there's more nitrogen floating around inside this closed container, and it's no longer in balance. It's no longer in equilibrium. So for a brief amount of time, it will shift to the right. More products will be made in order to bring it back to equilibrium. We're going to talk about this in terms of K in a little while. In Q, we'll do that in class. This is really just a shifting part. What if helium is added? Well, helium doesn't really impact either thing. Helium squirted into the syringe. Everyone says, "Hey, helium!" Voices go up high. They don't actually react with it because helium is a noble gas, inert gas, and noble or / inert gases don't react with things, so it's impacted equally. And there's no significant shifting to be contained. The container is made larger. This one is tricky. This one's really tricky. So let's say this container, which I drew here a little while ago, was magically made bigger. Oh, that worked out really well. So if it's made bigger, there's more space. There's going to be more and less collisions, or less collisions if it's made bigger. There's going to be a lot less collisions between everything. And usually you would look at these coefficients to figure out what's going on. But the coefficients end up being the same. Both sides are impacted equally because both sides have 2 moles of gas. 1 plus 1. Let me get rid of this. Nope, I can get rid of the whole thing. There's 1 mole of nitrogen plus 1 mole. There's 2. So this is 2 moles of gas, and that's 2 moles of gas. So both sides are impacted equally by this shift in the volume. If they had not been equal, like I have here in blue, if it had been 2 and 1, which is 3 versus 1, we would have a volume shift to the left because that side's the larger side. More on that in class. If the system is cooled, we need to look at the reactions enthalpy. This stuff right here, this is an endothermic because it's positive, it takes in heat. For this reaction to go this way, it has to take in heat. For this reaction to go this way, the reaction would be endothermic. So heat is put in. The heat plus these two makes that. But they're cooling it. That means they're taking the heat away. If I took this heat away, it's not going to go to the right. It's going to go to the left. So this reaction, in order to go to the right, needs to be endothermic. Heat needs to be added. They're doing the opposite of that. Another scenario, another Le Chatelier principle. We got a new reaction here. Hydrogen and oxygen make water. It's a very large explosion when this happens. Water is removed as it's being generated. If I take the water away, would it be an equilibrium? No, you can't be in equilibrium if you have reactants and no products. So without the water, it's not an equilibrium. So therefore, the reaction would start to shift right. And as it shifts right, it would reproduce the water and reduce the hydrogen and oxygen. Shift to the that's what that kind of is saying. The same in terms of Q, which we'll do it a Q perspective in class. What if hydrogen's added? Well, if there's too much hydrogen, again, it's not going to be an equilibrium, so it's going to react faster in the one direction and not the other, which would be to the right. What if the system is cooled? Well, let's look at this enthalpy value here. This is negative 484. That means it gives off heat as those two react. If I remove the heat by cooling it, it would shift even further to the right. Okay? That's basically what that says. We look at the enthalpy to diagnose which way it would shift, whether it's heated or cooled. All right, that is the end. See you tomorrow. Make sure you review those concepts.